All right, welcome to statics. We're just going to be doing one resolutant force with components. So we're going to break down a force into components and then find the direction and magnitude of those components. Before I start, I do want to let you guys know that I am a student. I'm not a professor. So that means that while I strive to give you the best answers and everything correctly, I do make mistakes. I'm not perfectly correct. So if you're using this to help you study and something's wrong, feel free to tell me. Just know that I am not like educated fully to give you the correct answers. However, I am very confident that I can do this very well. So that being said, this question, I'm just going to write some of the givens. It gives us that F1 is equal to 20 newtons. And it asks us to separate F1 into its components and then find those components. I'm going to do a little bit more than that. I'm going to find the components. And then I'm also going to find the magnitude, which is pretty much the same thing. I'm just going to use this term for the magnitude. And I'm going to find them using two different methods. One of them is I'm going to find it graphically. And this is the longer, more in-depth method. A lot of people might not have seen this. It's not typically used in statics that much, but I'm going to find it graphically, which is, I like graphically, even though it takes longer, it provides more detail as to why we're doing things or what we're doing. So it's easier for beginners to understand. And then I'm also going to be so this is method 1, and then method 2, I'm going to be finding it using it analytically, or however the hell you spell it. I spelled that wrong, but I'm going to be finding it analytically, which is going to be the typical way that you would see it in statics. Let me adjust this. So in statics, normally like using law of sines, law of cosines, finding exact measurements, that is what analytically is. But I'm going to be using both ways. So I'm going to show you graphically first, and then I'm going to show you analytically. So real quick to do graphically, I'm just going to redraw this line here. So it's going to be a vertical line, which represents V. And notice how V is at the top, indicating that this is the positive direction. Wherever the letter is the positive direction. So if V was down here, then downwards would be positive. However, V's at the top, which indicates that V is positive going upwards. And then I'm going to use my protractor to find angle, given that 105 degrees from the starting point. Let's go upwards a little bit. 105 degrees, so 90, 100, 105 right here. Is U. I have to give that. Extend it a little bit farther this way. All right. And notice how U is on the right side, which means that it's extending in the positive direction this way. So the force that we're dealing with in this question is asking about force 1. And force 1 is in the upper right corner, so both vectors would be positive. If force 1 was down here, one of them would be positive, one of them would be negative, and we can talk about that more later. Right now, let adjust this camera. All right, there you go. Now I'm gonna draw, now, before I draw anything actually, first of all, to explore something graphically, I'm using a ruler. It's a standard inch centimeter ruler, but the force that we're given is in newtons. So in order to express something graphically, I want to transition the newtons into something that I'm able to measure using my ruler. So a really good way that I like using is I just turn newtons to centimeters. Now, obviously, newtons don't turn to centimeters in real life, but we're just using this to express something in a graphical sense. So what I'm going to do is I'm going to say that every 5 newtons is equal to 1 centimeter. So what this does for me is that now, first of all, let me find the angle from the origin, 30 degrees. Right here. Okay. What I can do is I can now, I'm first going to lay a groundwork for where this line is going to follow. So it's going to go along this line, this angle, a 30-degree angle, all the way up to this point. And then I'm going to divide the 20 by the 5 newtons to give me how many centimeters it is. 20 divided by 5 is 4 centimeters. So obviously I'm just going to graph 4 centimeters along this line, which is about there. So this is force 1. 4 centimeters. Now, we have to express V and U in their components. So to do that, we're going to expand this. We're going to make a parallel line to V that makes a triangle, and we're going to make a parallel line to U. So I'm going to take one of these. I'm going to say, okay, here is U, make a perpendicular. And then now we can just shift this triangle forward and back to make a parallel line. So we connect it to the top of the force. And then we just, I'm gonna use green here, going to make dotted line there. So because this is parallel to U, we call this F of U. It's the component of F in the direction of U. And this would change depending on whatever your variables here are, X, Y, Z, blah, blah, blah. I'm going to do the same thing here. Going to make a perpendicular line to V. And then I'm just going to shift this until it intersects here. And then I'm going to draw a line here. All right, and then this is it's parallel to V, so it's the component of V in the direction, component of F in the direction of V. Now, a lot of people end up making mistakes. They just draw a line perpendicular to U to F1. However, that would be the projection of F1 onto U and not the component of F1 in the V direction. So don't confuse that. And if you don't understand anything of what I just said, don't worry. Just don't worry about it. You'll be fine as long as you use this strategy. Again, this is graphically, and then I'll show you analytically a little later. So graphically, this is all we have to do. We know that, first let me write that. I did not write my angles on here, my bad. We know that this is 105 degrees, and then we are given that this angle is 30. Okay. But graphically, all we have to do is measure the distance of these two lines. So we start 0, we go up, measure the amount of centimeters. Okay, let's see, this is F1u. And we're only gonna go, I actually drew these too far. So we're only going to go until the point, where did my ruler go? If I make this parallel line, we only actually want to connect the component at the end of the vector. So this is F1v, and then this is F1u. So these two are just intersections to show you how to do it. But these two lines here are actually what you should do. So I drew out this F1 all the way to the point just so I can draw it out. And then this one where it ends right here at the arrow is actually the length of it graphically. So I combine that graphically with this, and then I just use measurement tool, 0 here, go up to find it at like 3.2 or 3.3, maybe we could say. So I say that F1u is maybe 3.2 centimeters, and then F1v is see 1.9, looks like roughly 1.9 centimeters. Okay, now we just turn these, multiply them both by 5, because remember 1 centimeter is 5 newtons. So this would give me, you do the calculations, 3.2 times 5, 16 newtons. 1.9 times 5, 9.5 newtons. Okay. And that's all you have to do for graphically. Now, notice how graphically does not really give you very defined answers. Everything can change if you write the angle incorrectly, if you measure incorrectly, you don't get very defined answers. So this is a good way of knowing how to split things into components, but this is not really how you should be doing it in statics, and it's probably not how you were taught in statics. So now I'm going to do it analytically, and I'm going to describe the actual way that you would do it in statics. So still going to want to write out your graph here. V in the positive direction with, you don't actually have to have this angle perfectly for analytically, but I'm going to do it anyways. (105°). Okay, let me just draw this out and then I can get to it. All right, this is U, this is V. We have 105 degrees here, and then we have 30 degrees here. Now, the actual length for analytical does not matter. So you can just draw this out any length you want. I'm just going to draw it out to here. This is F1. And then we know that the degree angle here is 30. Okay. Really quickly, I'm going to draw out the parallel lines that we did using graphically. Again, with analytically, they don't actually matter the distance though. So we're gonna form parallel line, perpendicular, move this up, this would be F1u because it's parallel to the u, and it's the component in the u direction. And then this is F1v because it's parallel to v and it's the component of f in the direction of v. Okay, so now in order to determine this analytically, we need to know all the angles. So we can use properties of angles. So for example, F1v and FV are two parallel lines and they're being intersected by the line V. So because of that, we know that this angle here and this angle here are the same. So what that means is that because this is 105 degrees, it means that this angle here is also 105 degrees. And then to find this angle, all we need to do is 180 minus 105 minus 30, which gives us 45. So we know that this angle here is 45 degrees. Now, in order to actually solve this, you really only need one triangle. Like this, you can solve this question using just this. However, I am going to do the angles of both triangles. So using that same principle we talked about earlier, we know that F1v and V, two parallel lines intersected by F1. So we know that this angle here is the same as this angle here, which means that this is 45 degrees. U and F1u are two parallel lines being intersected by F1. So we know that this angle 30 is the same as this angle up here. So we know that this is 30 degrees. And 45, 30, 180 minus 30 minus 45 gives us the angle of 105 degrees. Now you can see that these two angles are the same. These two angles are the same. These two angles are the same. These two triangles are the same. If we know, what do we know about parallelograms? We know that 1/2 of a parallelogram is the triangle is 1/2 of a parallelogram. The area of a triangle is 1/2 the area of a parallelogram. So it should make sense that both of these triangles are the same. And they are. Because if you think about it, F1u, F1u. These two are technically the same angles, same lines. This line of F1u is the same line and the same length component as this line here that's on the axis. It's just offset. Same with F1v. The component of F1v is equal to the component of F1v here. So you can use either of these triangles. Like I said, I used both. I made both triangles just for you guys to see it, but you actually don't need it. And you can also double check these angles by taking the angle measurement of V. We know that a straight line is just 180 degrees. 180 minus 105, which is given to us in the equation, in the problem, 180 minus 105 equals 75 degrees. So we know that this angle from V to U as a whole is 75 degrees, and 45 plus 30 equals 75. So we know that we did that right. All right, now analytically, we use law of sines. So law of sines, remember, is, I'm just gonna draw a triangle here. If you have a triangle with A, B, C, sides A, B, and C, like told, and then we know that A divided by sine of angle A is equal to side B divided by the sine of angle B, which is equal to side C divided by the sine of angle C. This is law of sines. Now we can apply that here by saying, okay, we have ABC triangle, okay? We know that F1 is 20 newtons, so this would be 20 newtons over the opposite of F1 is this angle, 105. So it'd be 20 newtons over sine of 105. And then this will equal two different things. This equals, if we're trying to find F1v, then it'd be, okay, we don't know F1v, so we need to know F1v. Over, what's the opposite of F1v? 30. Sine 30. And vice versa, if we need to know F1u, we don't know that. The opposite of F1u is sine 45. And this work, you see how this works vice versa, because if I wanted to find F1v on this triangle, I know that this component here is F1v, and the opposite is just sine 30. So you can use both triangles, either one you want. Now we just pick and choose. So let's determine F1v first. So we're gonna remove this from the equation, and we're just gonna focus on here. Isolate F1v, the variable, on the left side. To do that, we need to multiply sine 45 to the other side. So we get F1u, my bad, not F1v. F1u equals 20 newtons over sine 105 times sine 45. Now this just equals F1u is 20 sine 45 over sine 105. If you plug that into a calculator, you get 14.64 newtons for F1u. Now, if we do that same method for F1v, ignore F1u, we have to isolate F1v, so we need to multiply sine 30 to the other side. So we get F1v equals 20 newtons over sine 105 times sine 30, which just simplifies to 20 sine 30 over sine 105. And if you plug that into a calculator, 30 sine times 20 divided by 105, you get 10.35 newtons. Now, if you compare these two, F1u 14.64 to, you have 16, it's similar. So we know that graphically, I must have overestimated F1u, because the real answer for F1u is 14.64 newtons. And then we have 10.35 newtons for F1v compared to the 9.5 newtons that we got for F1v graphically. So you can see how graphically you can get close to the answer, but you can't get the actual answer. Analytically is what we want to use in statics pretty much most of the time, unless you're specifically told otherwise. But this is pretty much how you would get the answer. Now, you have to be really careful here. If the problem asks you for the magnitude of the components, magnitude is always in an absolute value. So it would always be positive. So the magnitude of F1u is 14.64, magnitude of F1v is 10.35. It's always like that. However, if it does not ask you for the magnitude and it just asks for the component, then you have to include the direction. Now, like I said earlier, we don't need to worry about the direction because v is in the positive direction and u is in the positive direction. F1u is going this way and F1v is going this way. Positive, positive. However, if you had a force vector that was going this way, for example, notice how sorry, let me just do this really quick. F1u, which I'm drawing right now, is going to the left, which is going the opposite way of u, because remember, this letter over here indicates the direction of positive. So positive is to the right. This is going to the left, which means that the direction F1u is actually negative. You can do the same thing for v. Sorry, drew that badly. But F1v in this scenario is also going in the negative direction because F1v, or just v, sorry, v is positive in the up direction and F1v has to go downwards, which means that F1v in this scenario is negative. So if the problem asks you just for the components, you have to include if they're negative or positive. In our case, they're both positive. If you have a vector in this quadrant, up here, top left, then it would be given if v positive is up here and u positive is up here, then it'd be u negative, v positive. Like I said, this would both be negative, and then bottom right corner, it'd be u positive and v negative. This is also where you have to pay attention to what direction the positive is. A lot of times you'll find in graphs that v positive is down here and u positive is down here, which means that in this case, if we had the exact same problem, but the v positive was down here, then because F1v is going upwards, it'd be negative. But v is up here in this case, so we don't need to worry about that. So that's just a thing to look out for on all problems, is where the variables are, which way positive and negative is, and then if the question asks you for just the components, in which case you need to include negative, positive, or if it just asks you for the magnitude, then you don't have to do negative, positive at all. Just make sure they're both positive, because magnitude, like I said, is just absolute value. Okay, that's the entire problem solved graphically and analytically. Hope this helped you in some way. Good luck in statics.